Here are solutions to homework set number 10 for ECE 111. This homework set looks at capacitors. Now, a capacitor is an integrator. The BI characteristic is the voltage is 1 over C times the integral of the current. So if I have one paired capacitor, I just integrate. If this is the current, the voltage will be the area under the curve. Now, when you integrate, there's a thing called an integration constant. It depends upon where you start at. So kind of think about this like your checking account. If you start out $5 in debt and you do nothing, banks are really good. They will remember that you're $5 in debt. So take the old value, add nothing to it, and I still wind up at minus 5. Now, between 1 and 2, I add an area of plus 1. So take the old value, add 1 to it, and I wind up at minus 4. I now add 2. This area, width times height is 2. And I go up 1, 2, wind up right here. I now add an area of 1, 2, 3. So go up 1, 2, 3, right here. Add an area of 1, 2, 3, 4, plus 4. 1, 2, 3, 4, right here. Now at this point I add roughly an area of plus 2. And I go off the chart. Now start subtracting. When I'm below 0, I subtract. This has an area of minus 2.5, about. So come down 1, 2, 2.5. This has an area of minus 5. So 1, 2, 3, 4, 5. Area of minus 2.5. So here's 0.5, 1.5, 2.5. And then hold it. So that's what the curve looks like. Capacitors integrate. Takes the area under the curve. If it's positive, I go up. If it's negative, I go down. Each time you add a capacitor to a circuit, you get a first-order differential equation. So if I have this circuit, this is described by a first-order differential equation. That's part of the reason you take Calc 1, Calc 2, Calc 3 differential equations. To solve any circuit with capacitors and inductors, you need differential equations. To solve those differential equations, you'll do that when you take math. For this class, I will solve using Matlab and numerical techniques. The first step is I got to come up with a differential equation. To do that, for capacitor, I equals C dB dt, so I1 is C times the derivative of V1. From conservation of current, I1 is IA plus IB. IA is V0 minus V1 over 33. IB is 0 minus V1 over 220. So here's the differential equation that describes that circuit. And I'm using prime notation. Prime means derivative, just a little bit easier to write. Do some algebra, solve for the derivative. This is the differential equation that describes that circuit. Now, if the input V0 is a step that turns on at t equals 0, does that. 10 volts. Find the voltages. So I need to know the initial condition on that integrator. Kind of like with integration, I need to know where I start from. Since this has been 0 for infinite time before 0, this is discharged, V1 starts at 0. To solve, I can use numerical integration. So here's the Matlab code. I'm going to start with V1 being 0. Here's my integration step size, starting at t equals 0. I will run for 0.5 seconds. That's kind of arbitrary. I want to run long enough to see the transient, but not so long. Well, actually, here's the result. Anything after about 0.25 seconds is kind of redundant. Nothing's happening. So run it for 0.5 seconds. Here's my differential equation. At any given time, I know the derivative of V1 is 30 times V0 minus 34 times V1. That is this equation. Once I calculate the derivative, I know how fast it's changing. Move forward in time by 10 milliseconds. So I know the slope, that's dB dt. Here's dt. Multiplied by the step size, 10 milliseconds, and I wind up with this is how much the voltage changes. So it's the old voltage plus the change is the new voltage. That's at 10 milliseconds. Repeat. Go to 20 milliseconds, 30, 40, 50. Repeat until I get to 0.5 seconds. When I'm done, plot the voltage versus time. And here's what it looks like. What you've just done is you've solved a first-order differential equation using numerical integration and Matlab. Now the great thing about Matlab is without having had calculus, I can solve this differential equation. When you get to, I think it's Calc 3, maybe Calc 4, that's when you'll solve this by hand. There is an equation for that curve. Stay tuned until you take Math 266 to find that equation, but whatever it is, that's what it looks like. That's part of the power of Matlab and numerical integration. I can solve first-order differential equations just using numerical techniques. Okay, so that was fun. Let's check it in Circuit Lab. Build the circuit in Circuit Lab, do the time response. I'll simulate it for 0.5 seconds, 500 milliseconds, make the step size 1,000 times smaller, let her rip, and here's what you get. Same answer that I got in Matlab. And that's what Circuit Lab does. It uses numerical integration. I don't really know what kind of integration it uses. Probably much better. I'm guessing Runge-Kutta. There's better integration than Euler that we're using. But I use Euler integration because it's simple. It's not too bad. What Euler integration does is if I have a curve like this, I split it into rectangles. Width times height is the area under the curve. A little bit wrong, but simple. There's better forms, but more complicated. So anyway, that's one-stage filter. All right, now that I can do a one-stage filter, let's do a 10-stage RC filter. So with the 10-stage RC filter, I've got 10 capacitors. I've got 10 first-order differential equations that are coupled. To solve, I want to integrate. So kind of going a little bit ahead of ourselves, here's what the integration is going to look like. At any given time, I know the voltages. Here's my input voltage, 10 volt step on the left. I can calculate these are the differential equations. Find the change in V1 through V10, integrate, move forward in time, and repeat. Now to do that, I need to know what these numbers are. That's a function of your circuit. I need to come up with that differential equation. So to do that, do the same thing we did before. By symmetry, all the nodes are the same except for node 10. So if I find the node equation, differential equation at node 1, it's the same differential equation everywhere, just increase the index. That's kind of what this code does. Same differential equation everywhere, just increase the index. So let's take node 1. The current I1 is C dB dt. I1 is IA plus IB plus IC. IA is V0 minus V1 over 33. IB is 0 minus V1 over 220. IC is V2 minus V1 over 33. All that is C dB dt. Do some algebra, solve for V1, the derivative of V1, group the terms. Here's what you wind up with. That's the differential equation at node 1. Node 2, 3, 4, up through 9 will all be the same, just increase the index. So that's what the Matlab code does. I get the differential equation at node 1, 2, 3, 4, 5, 6, 7, 8, 9. 10's the oddball. The reason 10's the oddball is I don't have this extra resistor right there. So what happens is this term goes away. I just have two terms. I've got two resistors attached. I have two terms. Doing some algebra and solving, you wind up that the derivative of V10 is 30.3 V9 minus 34.84 V10. So node 10 is a little bit different. Those are the differential equations that describe the system. You can also impress your friends and roommates. You are solving a 10th order differential equation in this class, which actually isn't that bad. Using Matlab, it's not that hard. To find the voltages, I want to solve. To solve by hand, stay tuned until you take Math 266. And this class, we will solve using numerical techniques in Matlab. So what I do, I'll show you. I give it an initial condition, so all the voltages are initially 0. I move forward in time, calculate the derivative, how much the voltages are changing, integrate, plot it, and repeat. So here's what that looks like. Let this rip. These are the voltages at node 0, 1, 2, 3, and so on. Here's my time marker. It's now 4 seconds, 5 seconds. At 5 seconds, I can show what the voltages are. So what happens is V0 jumps at 10. This is V1. V0 charges up capacitor 1. That charges up C2, charges up 3, 4, 5. Might show a little better. Let's just bring this out to 1 second. Make the step size a little bit smaller. Let her run again. So here's your V0, charges up V1, charges V2, V3. This is also temperature. RC filters are coupled first-order differential equations. That's also called the heat equation. This is how temperature behaves. Make the left side 10 degrees Celsius. Here's the heat propagating down the bar. Then if I plot temperature versus time, or voltage versus time, that's what I get. You've just solved 10 coupled first-order differential equations, or a 10th-order differential equation net. And the corresponding Matlab code. Again, where these numbers come from, that's from the circuit. Every circuit is described by a different differential equation. You got to analyze the circuit to find out what that differential equation is. Once you find it, I can solve using Matlab. In Circuit Lab, I can do the same thing. Build the circuit. I only went to 3 nodes because I was lazy. Good enough for the homework. If I do numerical integration, simulate it for 2 seconds, step size 1,000 times smaller, and plot it, that's what I get. Here's V0, 1, 2, 3. Kind of the same idea. Little different because I'm missing the other 7 nodes. But that's what Circuit Lab is doing. It's using numerical integration, just like we did in Matlab. The final problems look at eigenvalues and eigenvectors. Now the reason we're doing this is very few people understand what eigenvalues are. Even fewer understand what eigenvectors are. These are topics covered in Math 129. An eigenvalue is defined as A minus lambda I. When is that determined at 0? Those are the eigenvalues. The eigenvector is A times the eigenvector is the eigenvalue times the eigenvector. Okay, so what's that mean? That's the problem with Math 129. They've got to make it generic, so they can't really favor any majors. Well, in this class, this is for electrical engineering. We can favor electrical engineers. Let's look at the eigenvalues, eigenvectors for this system and see what they actually are. Kind of the hope, probably kind of confusing. The hope is that when you get to eigenvalues, eigenvectors, you can refer back to this and kind of have some concrete system to think about. Now, if I take the differential equations for this system, like so, put it in matrix form, notice that dV1 is minus 60.5 V1, dV2 minus 60.5 V2, dV3 minus 60.5 V3. This is diagonal, minus 60.5 on the diagonal. Put this in matrix form, that's the diagonal entries. So your dV is that times V. The off-diagonal entries are 30.3, 1 and 3 for 2, 2 and 4 for 3. Those are these numbers. The off-diagonal is 30.3. Put that in matrix form, I get a 10 by 10 matrix. And it's actually not that bad to put into Matlab. I'll start with the zeros matrix. Those terms are 0. The diagonal is minus 60.5, off-diagonal 30.3. Put that in for loop. The oddball's right here. Put that in manually. Here's my 10 by 10 system. Now in Matlab, a 10 by 10 system has 10 eigenvectors. It has 10 eigenvalues. The eigenvalue is how it behaves. Eigenvector is what behaves that way. So something decays really, really fast, decays at e to the minus 123t. What that is the eigenvector. Something decays really slow, e to the minus 5t. What that is the eigenvector. So let's go back to Matlab. Let's make the input forcing function 0 and give it some initial condition. Like, let's make the initial condition all ones. If I plot the response, it starts out at 10 volts, and then the voltage drops. What happens if I change the initial condition? So at the start of the code, I input my A matrix. That's our 10 by 10, minus 65 on the diagonals. 10 is kind of the oddball. Let's find the eigenvalues, eigenvectors. Let's make the initial condition the fast eigenvector. That should decay as e to the minus 123t, so let's try it. Marks, get set, go. Try it again. Marks, get set, go. Poof. Gone. Now what you're seeing is the eigenvalue and eigenvector. The shape is the eigenvector. If you notice, the shape stays the same, that plus minus, plus minus, plus minus. The shape is the eigenvector. The amplitude is the eigenvalue. The amplitude is dropping down as e to the minus 124t, the eigenvalue. 123t. Let's take the slow mode. If we make the initial condition the slow eigenvector, that's number 10, let her rip. The shape is the eigenvector. The shape stays the same. I've only excited one eigenmode. It is decaying as e to the minus 5t. Really slow. And there's 10 eigenvalues, there's 10 eigenvectors. Let's take the next mode. Mode number 9. The shape is the eigenvector, that's up here. The eigenvalue is how it decays. This will decay twice as fast, e to the minus 10t, and the shape is that. Shape is the eigenvector. The eigenvalue is how fast that decays. And there's actually 10 modes. Let's take mode number 8. This decays as e to the minus 20t. And the shape stays the same. The amplitude is the eigenvalue. Mode number 7. That decays as e to the minus 34t. That's what eigenvalues, eigenvectors are. They're the mode shapes and how fast they decay. So what happens if I make the initial condition something random? The last problem on the homework. Let's try it. There's my random initial condition, and fairly quickly it decays to this shape. I recognize that shape. That shape is the slow eigenvector. And it's not just random, it happens every time. What's happening is they give it a random initial condition. All 10 eigenvectors are excited. The fast modes decay quickly, leaving the slow mode. So what I'm looking at is an eigenvector. Here's all 10 eigenvectors, quick ones go away quickly. What I'm left with is the slow eigenvector. And kind of show that again. This is the slow eigenvector, same shape. That's kind of an idea of eigenvalues, eigenvectors. Kind of confusing, but when you take linear algebra and they talk about eigenvalues, eigenvectors, and they give you the definition, to me that means nothing. Think about this problem. The eigenvalue is how the system behaves. The eigenvector is what behaves that way. I've got a 10th order system, there's 10 eigenvalues, there's 10 eigenvectors. And you can excite the fast mode, or here's the slow mode. I could excite the fast mode. There's the fast mode. Or if I excite everything, what you wind up with is all 10 modes being excited, the fast modes go away quickly, leaving the slow mode. So this actually is an eigenvector. That's homework set number 10 for ECE 111. Capacitors, and when you have capacitors, you have coupled first-order differential equations. Power of Matlab is I can solve coupled first-order differential equations using numerical integration. And that's homework set number 10 for ECE 111.